Hi all of you, welcome back. So today again we are back again with another video on the concept clearing classes from NewtonGATE. So today's topic, as you can see, is going to be calculus. To be specific, differential calculus. Now this particular topic has been a constant support for all the aspirants of mains and advanced. This chapter is not only important but also it can be helpful for many other chapters like limits, maxima, minima, and also in parts of your integral calculus. Now this chapter is very easy if we understand the basic concepts of it. So without further ado, let us start with the video. So first of all, the name calculus. Now from where did it actually originated? So calculus actually came from the Latin word meaning small stone. Now there are two different types of calculus. One is differential calculus and another is integral calculus. Now the main difference between differential calculus and integral calculus, what is that? So differential calculus is when we have a bigger picture and we cut it into smaller pieces. Like for example, suppose we have over here a curve like this. Now, or suppose a curve or a figure like this. Now, suppose we are dividing this into equal parts, and we are finding the position or the area of each individual parts. So here what we are doing, we are dividing the whole bigger picture into smaller pieces and then looking at the changes what each of the smaller one is going through. But in integral calculus, we just do the opposite of it. What we do is we again collect back the smaller pieces and then finally whatever the result is, we go through that. So here to explain further the differentiation reason, why do we actually need it in our day-to-day life, I have taken an example. So here Sam will do a jump off from a 20-meter building. Now Alex as a photographer asks him, how fast will you be able to fall after 1 second? Now Sam what he does is he uses a very simple formula, and this is d equal to 5t square, which comes from the formula d equal to half gt square, where g we are taking it to be 10. So applying that formula, the gravitation is doing its own work. So the distance he will fall is 5t square. So at 1 second Sam will have fallen by 5 into t square, that is 5 meter. But that is the distance he is falling. But if you remember, the photographer asked how fast can he fall down. So we know that the formula for speed is distance by time. So if we take at 1 second time, he will be falling at 5 meter per second. But says Alex. Now Alex was in a confusion. He said that is an average speed. That is when I am taking that I will fall at a regular speed of 5 meter at every equal intervals. Then it is 5 meter per second. But if I want to find my exact speed at the particular exact moment when the camera was clicked, so that I can set up the camera properly. So at the exact 1 second when the camera needs to be clicked, if I have to find the speed, what is that? So as you can see, we are taking the initial and the final speed divided by minus the initial distance minus the final distance, or final distance minus initial distance. So here at 1 second Sam has fallen through 5t square, where 1 is the time and hence it is 5 meter. But if the question is how fast is that? So there we need to know the speed. So speed is distance over time, and if we apply the distance, that is 5 meter, and at time 1 second, then the speed is 5 meter per second. But now Alex is saying that is an average speed. That is an average speed when we are taking that at each interval of time you are jumping at the same speed. But I want to know at exactly 1 second where you will reach or what will be your speed, so that I can set up my camera properly. Now, as we know, the formula for the speed is final distance minus initial distance divided by final time minus initial time. Now, here let us go back, and we have to see that exactly 1 second. Now, exactly 1 second means what? So here we are saying that exactly 1 second means that the initial as well as the final time is 1. Now, at 1 second we know that the distance covered was 5 meter. So my initial as well as my final distance is the same case for your time. So 0 divided by 0, we don't know, it's a infinite value. Now the speed is not is a value which is attainable. Now what exactly happened here, and how can we solve this problem? This is where our differential calculus comes into help. Let us see how is that. So we have nothing to calculate with. Now what we are going to tell is 1 second is a very small time. Okay. Now Sam said what we do is take a very small amount of time so that it won't even matter. Matter as in it will not have such a huge difference in my whole outcome. But it will still give me a clear idea for exactly at 1 second. Now what he did was, he invented the time or said the time to be delta t. So what happened here? At 1 second, Sam had fallen 5t square. Now delta t was a very small amount. What he did, if I add, even though at the first second he had fallen 5 meter, now there must be a slight difference from that 1 second, which physically is not easy to interpret it in human's eye, but that exists. So at 1 plus delta t second, the same thing, instead of t, we will now put 1 plus delta square. Now we can expand 1 plus delta square using the formula of a plus b whole square. A plus b whole square, where a square plus 2ab plus b square. So here I am taking a as 1 and b as delta t, and we are getting this same expression. Now this was at 1 plus delta t, how much distance he has actually fallen. So we are actually putting the expansion over here, and then we are multiplying this. Now if we go back and see, at exactly 1 second he had fallen down 5 meter, and at 1 plus delta t he had fallen this meter. Now what exactly happened here, and what was the problem that we couldn't solve in the previous position? Now previously, if you remember, at exactly 1 second, my final as well as initial distance and time was remaining same. But after introducing a small amount of time which will not hamper the whole process, I am getting my distance something which is different from the previous distance. So here I have shown it pictorially. Here at t equal to 1, this is the position, and let delta t be a very small amount of time like this. Okay. So here t is 1 plus delta t. Now in summarization, if I have to say, then 1 second it has travelled 5 meter, and in 1 plus delta t he has travelled this much meter. Now as you can see, there is a slight change in the distance. So change in d, we are subtracting the final distance minus the initial distance, and we get the following equation. Now if we have to calculate the speed, which was actually the problem we were facing in the earlier condition, we can now see that we have a change in distance and also a change in time, which gives us 10 plus 5 delta t meter per second. Now if you remember, delta t was a very small value. It was something which was shrinking towards 0. That means a value of time which will not cause much difference in the whole situation. In this case, if we see it is shrinking towards 0, what we can do is 10 plus 5 delta t as in 0 meter per second, which gives us the result 10 meter per second. So yes, we are getting an actual answer which is 10 meter per second. So this is how calculus helps us. Now calculus helps us, or differential calculus helps us to find the position or an area or the speed at a very slight changes of time, which is physically not possible for us to calculate. Now with that, let us go through some other examples where we can do the same thing or same knowledge. So here we applied, as said, we applied the condition of differential calculus to cut time and distance into small pieces so that a pure answer can come out. Now let us try to do that, the same thing for a function y equal to x cube. So here we have to find what is the slope, or what is the slope of the function y equal to x cube at x equal to 1. So here what we are doing, first of all, this is a curve of y equal to x cube. Now this point 1 comma 1, we will find the slope. Now if you remember, slope was change in y by change in x. Now let us first understand why it was difficult to find the value in the first case if we find the value of slope. Now slope, as I said, it is change in y divided by change in x. Okay. Now at x equal to 1, y equal to 1. So at 1 comma 1 we are getting 1 minus 1 divided by 1 minus 1. So for starters, let us find the slope of the function y equal to x cube at x equal to 1. Now as given, it is the graph of the function y equal to x cube, and we are to find the slope of the function at x equal to 1. Now at x equal to 1, y is 1 cube, which is again equal to 1. So this is the exact position where we have to find the slope of the function. Now again at x equal to 1, we know the value, and x equal to 1 plus delta x, taking delta x to be very small quantity, we can expand it again using the formula of a plus b whole cube, which gives us this formula. Clearly you can see that from x equal to 1 to x equal to 1 plus delta x, there has been a change, and this is that change. Now this particular process is also known as differentiation by first principle. Differentiation by first principle, where we have delta x as a very small quantity. In some topic or in some books, you can also find it to be delta H. It basically means the same thing. If we are just taking whatever value which is nearing towards 0 or has extremely small amount. So slope is, as we know, change in y divided by change in x. So this is change in y and this is change in x. Now we get 3 plus delta x and delta x square. Now taking delta x to be 0, tending towards 0, we find the value of slope equal to 3, and this is the slope. Now what would have happened if actually we have taken the slope from the graph? Now how can we find that? Now the slope, as you can see from the curve, it is continually changing, but exactly at the point 1, 1, you can draw a line to the tangent of the curve and you can find that the slope is actually 3. So we can say that the process by which we can find the slope is as clear as we had used in the differential calculus. Again, this process is also known as first principle, differentiation using the first principle. So with that, we have introduction to derivatives, and it's all about slope as we had done before. Basically what we are doing here is we are finding the slope of particular curves, which means that change in y divided by change in x is actually what is derivatives. Now derivatives are very small, they have to always shrink towards 0, and that is why derivative is taken as del y by del x, where both del y and del x are shrinking towards 0, but they are not exactly 0, they are pointing towards 0, something which will have no effect on the whole scenario, but yes, it is not exactly 0. So here we have found the process of derivatives, change in y divided by change in x. So I have taken a function and here this is the function fx, and here at this point it is fx, and a slight change in distance is fx plus delta x. So x has changed from this position to this position, so this is delta x, and y, or that is fx, has changed into this position which is delta y. Now according to the slope formula, if we find out the slope formula, we get this as our equation, and as our delta x will be shrinking towards 0, we finally get the equation for the formula. Again, using the same principle of differentiation, we are now finding the example or function of x square. So this is a typical situation or typical example of differentiation by first principle. Now instead of x square, we can have any amount of function. You can apply the same process. Just remember that instead of x here, in this case, you will put the function. Like here in case of x square, if suppose we have another function, let's say 3x plus 2, suppose. Now in that case what we are going to do is, let's say fx is equal to 3x plus 2, then fx plus delta x. Now see, here we are only changing the x value, we are not changing the 2 values. So what will change is 3x plus delta x plus 2. We are not changing the 2 because 2 here is a constant. Okay, so what is changing is 3x plus 3 delta x plus 2. And again you will repeat the same thing, and in the down we will have delta x, and finally we will take everything. Delta x will always tend towards 0, and finally we will get the slope to be 2x. So this is by first principle formula. The derivative is now written as commonly as d dx. So d dx of x square is 2x, or the derivative of x square is 2x. Now d dx is also represented as f dash x. So this is the first derivative which is written as f dash x. Now going forward, we will also learn about other differentiation. We have second order differentiation, we have third order differentiation, and so on. What happens in those cases, either if you are writing in this form d dx of x square, in this case it is just the first order differentiation. If we further go to differentiate, the process and everything will be same. Now what will happen is, instead of writing it in this form, in second order differentiation, what we do is we just put our 2 inside of this. This means that we are differentiating x square, the function x square twice. And if I have to write in this form, it is f double dash x. Now once we have found out the required order of differentiation, our sum is good to go. Now in this case, we have to find the slope or the rate of change at any particular point. Now we know that any particular point it is 2x. Now if it is given at a particular point, let's say maybe here like x equal to 2 or x equal to 5, we can just put the required value here and we will get the equation answer. Okay. So that was what we know as the first principal rule. Now we have some general derivative rules for all the functions. For any constant function, the derivative will always be 0. For a linear equation, that is a function x, it is 1. For a function ax, it is a. For a square, it is 2x. For a square root, it is half x square, x minus 2. Exponential, it is e to the power x. Logarithmics, this is the value. Sin x, cos x, tan x, and these are the inverse formula. Now for algebraic equation, we have any kind of algebraic expression. There is a general rule which is, suppose d dx of a x to the power m, where a is a constant. We will be coming to that in a second, but here is what we have. Now a x to the power m is a m x m minus 1. This is a general derivative formula for all the algebraic expression. So the derivative of sin x is cos x, or we can also write sin x dash is equal to cos x. Now the rules for derivatives are quite simple. It generally follows, this is the power rule, multiplication is generally the c is a constant and c into f dash, product rule and quotient rule. Sum and difference rule are very easy. You just have to add the differentiation part of individual items and then go forward. Chain rule, again it is for your composition of function fog into g dash, and again chain rule using d dx is following the same thing. The most important are the product and the quotient rule. So let us go through some sums which will be requiring this kind of rules. Here we have taken the power rule where d dx of x cube. Here n is equal to 3, we are using the power rule, and using the power rule we get 3x square. Next again we have a power rule 1 by x. Here the power of x is equal to minus 1, and using the same formula we will get 1 minus 1 divided by x square. Whenever the power will come, you always try to bring it in this form and then apply the power rule. Multiplication by constant and sum rule. So multiplication of a constant, it changes nothing. The constant remains as it is, just the variable part will get differentiated according to the power rule, or maybe if it is a trigonometric function, it will get differentiated into trigonometric function, and so on. And same for your sum and difference rule. Sum rule also, the individual variables we will differentiate, and then the result will be added as follows. The difference rule is same as the sum rule. We will individually find the rules or the differentiation rules of the individual functions. It may be a logarithmic functions, it may be a trigonometric function, it may be an algebraic function, but we will find it in a same manner, and then the result will be subtracted. Same goes for constant, multiplication and power rules. Okay, now what is the derivative of cos x into sin x? Now this is where we have the product rule. Now product rule, we have to first segregate into two functions, one is fx and another is gx. Now the product rule is fg dash plus f dash g. Now we can interchange f and g. You can take sin x to be g, you can take fx to, cos x to be f, and so on. We can always interchange. But whatever we do, we have to put it in this form. So here I have taken f as my cos x and g as my sin x, and this is the result I am getting. Now let us see what would have happened if I had taken the opposite case. That is, if g would have been cos x and f would have been the sin x. Would that be any different, or it would have been the same thing? Okay, so sin x, now cos x is minus sin x plus cos x minus sin x. Sorry, f dash is cos x into cos x. So minus sin square x plus cos square x. So technically we are getting the same result. So in product rule, it doesn't matter which function we are taking the first. It is commutative, and hence we can take the function as our wish. But that is not the same for our difference or quotient rule. In quotient rule, we have to remember that the derivative of high to over low is always the f and g has to be constant. We cannot change it. That means the numerator will always be my fx and my denominator will always be my gx. We cannot interchange them. Okay, and then following the rule we can differentiate. Reciprocal rule is another part of our power rule. Instead of reciprocal rule, we can convert this into x to the power minus 1 and still can get the same result. So reciprocal rule is a part of our power rule, or we can say it's a branch out of our power rule where all the powers are in our denominator, or we have negative powers. Chain rule. Now chain rule is, now before starting with chain rule, we want to discuss something very important. Now what exactly is chain rule and where do we have to apply it? Now chain rule is very different from the product rule. Okay. Now where exactly do we have to use the chain rule? So whenever there will be a composite functions like this given, where there are two different kinds of function, different kinds. It's not like x square into x to the power 5 or maybe tan x into x cube. Now here see, we have two separate kind of functions, but they are separated entirely different. Now in this case, there are two different kinds of function, but one is integrated or one is composite function of the another. Okay. So we have a trigonometric function as well as we have a function of algebraic function. So here we have two functions over here, but the difference is they are not in product, they are the composite functions. So in terms of composite functions, then we apply chain rule. Now while applying chain rule, always remember that we differentiate from outer to inner. The function which is given outside is always differentiated first and then slowly we get inside. Like for example, in this case, it is sine x square. So first of all, we will differentiate sine, which is cos x square. Then sine totally is done, it is differentiated. Now we get to x square and we differentiate x. So this is our final answer. So always remember, always differentiate completely from outer to inner. First of all, differentiate the outer function entirely and then come to the other functions which is given inside. Now this is all for our differentiation rule. We have completed all the differentiation rule. Now if you have understood the concept, let us try to solve this type of functions and try on your own, and if you have any queries you can contact us in the following details. If you like this video, if you enjoy this video, please give like, share and subscribe, and for more details visit our website NewtonGATE.in or call us on the following numbers. Thank you and let us see in the next video. Thank you.